In this video, we will talk about geometric series. So I want to motivate this with an example. So suppose I have the sum 5 plus 15 plus 45 plus 135 plus, and it looks like there's bigger and bigger terms after that. This is something called a geometric series, and what that means is there's a pattern to get from one term to the next. To get from 5 to 15, I multiply by 3. To get from that to 45, same thing. Multiply by 3. To get from that to 135, I also multiply by 3. And I keep going like this to get to the last term. I still multiply by 3. So in part A, what I want to do is express this sum in sigma notation. And B, I'm going to see, well, what is the actual sum? Like, is there a nice way to add up all these terms together that doesn't involve like actually just like doing it one at a time and adding them together? Okay, so in sigma notation, I know I'll have my sigma. And what I'm noticing is all of these terms, they kind of start with 5, and then they're multiplied by a bunch of 3s. Like, to get 15, I multiply by 1 3. To get 45, I multiply by 2 3s. And if I keep counting it down like this, then it would be 3, and then 4, 5, 6, 7, 8, 9. 9 total 3s have to get multiplied to get the last term. So all of my terms kind of look like 5 times a bunch of 3s. So I'm going to write 3 to the I power, where eventually I need I to be 9 to get to the last term. And where I need to start it off is letting I be 0, because the very first term hasn't gotten multiplied by any 3s yet. And if I plug in 0 for this, 3 to the 0 is 1. So I do end up getting 5 for the first part. Okay, so let's now compute the sum. So there's a very famous proof for how we get the sum of a geometric series. In fact, it's one of my favorite proofs. So let's go over how it works. What I'm going to do, noticing the fact that, to get from one term to the next, I always multiply by 3. Let's just multiply both sides of this by 3. So I'll get 3s on the left. On the right, if I multiply 5 by 3, I get 15. And I'm going to write that underneath this 15 on the top. If I multiply 15 by 3, I get 45. And I'm going to write that underneath the 45. And if I keep going like this, whatever the term before this one was, if I multiply that by 3, I would get 32805. Multiplying 32805 by 3, I get the 98415. If I multiply that by 3, I'll get something new. But let me use the fact that 98415, well, that's just 5 times 3 to the 9. So if I multiply that by one more 3, I would get 5 times 3 to the 10. And I could work that out if I really wanted to. It's some 6-digit number, but let me just leave that like that for now. So seeing that there's so much overlap in these two lines, let's subtract them. I'm going to subtract these, because if I subtract them, I get a bunch of cancellation. The 15s cancel, the 45s, these do, and there's just a couple of terms left over. So on the left, I get s minus 3s. On the right, I'm left with 5, and then minus 5 times 3 to the 10. And I could simplify the left-hand side to negative 2s. Let me deliberately keep it like this for now, because it's going to generalize to a formula, which I'll point out right after this. Instead, if I factor out s from the left, I get s factored out times 1 minus 3 equals, I can factor a 5 out of the right and get 5 times 1 minus 3 to the 10. And then I divide this thing in the parentheses, and I get s will be equal to 5 times 1 minus 3 to the 10 all over 1 minus 3. And it turns out if we work out what this is, if we work this out with a calculator, we get 147,620. Okay, so one thing we might be wondering is, well, why bother doing this whole derivation if ultimately all I was going to do was just plug it into a calculator at the end once I had this fraction? Well, the reason for that is, what if instead of having 10 terms like I do now, what if I had 100 terms? Plugging that into a calculator will take a really long time. But plugging into a formula, if I can get a formula for something like this, is very quick. In fact, we are ready to state the more general formula. So this is something called a geometric series, when I get from one term to the next by continuously multiplying. So in my geometric series, the formula of my terms looks like this. Some number a, and then times some number r to the I power. And if I start at I equals 0 and I plug that in, I'll get a, because r to the 0 is 1. If I plug in 1, I get ar. If I plug in 2, I get ar squared. And if I keep going like that until I plug in n, I'll end up with ar to the n at the end. So I'm getting from one term to the next by just multiplying by r, multiplying by r again, and so on and so on. And I can generalize the formula that I got here to the formula for the sum of a geometric series, where this number a, for my problem, that was the 5, what that represents is the first term. That is the first term of my overall series. And this other number r that shows up in the general formula is what's called the common ratio. That is this number I keep multiplying by to get from one term to the next term. Okay, so there we have it. There we have our general formula for the sum of a geometric series. So the question I want to end the video with is, why in the formula do I need r to not be equal to 1? So that was a detail that I hadn't really mentioned. Why is r not supposed to be equal to 1? Well, if I were to plug in r equals 1, if I were to plug in r equals 1 into this, I would be dividing by 0. So if r equals 1, we're dividing by 0. We are dividing by 0, which we can't do. Okay, so that's why I need r to not be equal to 1 for this. Like in my problem, when I was doing it in this example, if r was equal to 1, that would mean instead of this being a 3, it would have been a 1. And then this thing in the parentheses would have been 0. So when I divided it, I would have been dividing by 0, which is a no-no. I don't want to do that.